Welcome back to part 3 in our series about optimization, where we are going to discuss, I did it again, how much time can we save? And believe it or not, there's actually a mathematical formula that can tell us exactly this. It is called Amdahl's law. Now, Amdahl's law was originally developed to describe how much parallelization can save in a program's running time. But we can generalize it a little bit, which we're going to do in this video, to talk about not only optimizations that come from parallelizing code, but also, that's a very difficult word to say, but also just from general optimizations. And here's the formula. T is the amount of speed up that you can get from a particular section of your program. It's going to be equal 1 over 1 minus P, where P is the proportion of running time of that part of your program, plus P over S, where S is the amount of optimization that you can get from that part of your program. So let's write those down over here so we can remember. P is the proportion of a program that's subject to optimization. And in a slightly different color, S is the amount of optimization that we can get from that particular part of a program. And to try to illustrate this, let's draw out a simple execution of a program. Okay, something like this. And the program is going to have 3 parts, A, B, and C. It's going to run through part A first, and then through part B, and then through part C. So for a game engine, this might represent a single frame of your game. And maybe first we execute the game logic. That's part A. Maybe I should have called it part G. And then we're going to do the physics, and then we're going to do the rendering. And we want to know how much we can make this program faster by analyzing the properties of each one of these 3 sections of the code. So let's say that part A takes 0.3 proportion of our program. In other words, 30% of the time part A will run. That is the game logic. 0.4 of the time, in other words, 40% of the time, the physics will run, and 0.3 of the time, the rendering will run. And we know, using techniques that we're going to learn in some future videos, that we can increase the game logic by 3 times as much. We can make it 3 times faster. And we can increase the physics, that should be a B, by 2 times as much. But we haven't hired any rendering engineers, and so we don't know how to increase the speed of the rendering. And so this on the left is going to be our P. Okay, that's going to go into the P parameter of our formula, and these on the right, you guessed it, they are your S's. You're going to go into the S parameter in our formula. So let's start calculating. Let's see how much time we can save in game logic given how long game logic takes to run and how much we think we can optimize it. So P in this case is going to be 0.3, which is the proportion of time that we spend running the game logic. And so we add that to 0.3 over S is going to be 3. And then we simplify this. We get 1 over 1 minus 3 is 0.7, plus 0.3 divided by 3 is 0.1, which equals 1 over 0.8, which is 1.25. Great. And now let's do again, I write A when I mean B. Now let's do the physics. We want to know what kind of speed up we can get from the physics. So we're going to go 1 over 1 minus. Now we have P is 0.4 plus 0.4 over 1. I'm sorry? That is going to be over 2. Because the physics part, from the physics part of our program, we think we can get a 2x speed up. Simplifying this, we have 0.6 plus 0.4 divided by 2 is 0.2. Lo and behold, we have 1 over 0.8, which is 1.25. So even though we have very different numbers here, even though our game logic takes less time than our physics to run, since we can get a better speed up out of it, it turns out the game logic optimizing our game logic will get us just as much leverage as optimizing our physics. So now let's take it a step farther. Let's see further. Let's see what is the maximum speed up that we can get, TA max, from optimizing our game logic. Let's say we put it in some kind of infinite quantum computer or something and got it to take 0 time to run. And the reason I'm doing this little thought experiment is so that we can see asymptotically what is the maximum available optimization to us. It's just a thought exercise. So we're going to use this should be 0.3. I can't talk and write at the same time. So 0.3 plus 0.3 over, we're going to put a really seriously big, we'll just put infinity here, okay? That represents, let's say we put it in that infinite computer and we got infinitely better running time from just the game logic. What that's going to do is it's going to make this term, 0.3 over a very large number, that's going to make this term just go away completely, and now it's 0. And so that's going to be just 1 over 1 minus 0.3, which is 1 over 0.7, which is about 1.4. Okay, and let's do it again for, put that back. Let's do it again for B. Let's see the maximum speed up that we can get out of the physics part of our program, part of our game. We do the same thing. We say 1 minus 0.4, because now we're using 0.4 because we're examining the physics instead of the game logic. 0.4 over infinity. This part goes to 0. We have 1 over 1 minus 0.4, which is 1 over 0.6, which is about 1.7. So you see we can get much more speed up if we focus on the physics, which makes sense because the physics takes up the largest part of our execution time right here, 0.4, whereas the other two sections take up only 0.3. So the big takeaway here is when we're deciding which part of our program we want to optimize the most, we go for the biggest slice. What is taking up the most time? And I mean, this seems like an obvious conclusion to make, that you look at the thing that's running the most and you optimize that. But it's not always that simple, because as you can see, even if something takes a little less time to run, maybe you have a better optimization for it, and so it makes it more worth it to focus on that thing. Now, I don't think that most programmers explicitly do this formula when they're considering what optimization to run, because one, who likes doing all these formulas and stuff? But two, you don't always know exactly what kind of speed up. You don't always know this term. You don't always know exactly what speed up you're going to get from one optimization. But after you've done many optimizations, you kind of gain a sixth sense for how much time you can save doing any particular optimization. And so it means you can kind of guesstimate what sort of speed up you're going to get by looking at each part of your program, because you kind of do this formula subconsciously in your head after you have enough experience. Great, so next week we are going to get a little bit less theoretical and start learning some specific techniques that we can use to optimize our programs. See you then.